Hello friends, welcome to the lecture on solution of homogeneous linear system with constant coefficients. In this is our second lecture on solution of homogeneous linear system with constant coefficients. In the previous lecture we considered the case where the characteristic equation had an distinct real real roots. All the roots of the characteristic equation were real and unequal. Now we shall consider the case where the characteristic equation has complex roots. So then how we shall find the linearly independent solution of the vector differential equation x dot equal to x. So let us consider the case where suppose lambda equal to alpha plus I beta is a complex eigenvalue of A with eigenvector v equal to b1 plus I v2. Okay. So here what we are assuming is that the characteristic equation determinant A minus lambda equal to 0 has a complex root lambda equal to alpha plus I beta. If lambda equal to alpha plus I beta is a root, lambda equal to alpha minus I beta is also a root, because we are assuming A to be a real matrix. So first we consider the case where lambda is equal to alpha plus I beta, and we assume that the associated eigenvector A b equal to lambda b for lambda equal to alpha plus I beta, okay, gives you b equal to b1 plus I b2. Okay. So b equal to b1 plus I b2 is an eigenvector of A corresponding to the eigenvalue lambda equal to alpha plus I beta. So then x t equal to e to the power lambda t into v will be x t equal to e to the power lambda t e to the power alpha plus I beta into b. So b1 plus I v2. Okay. So it is a complex valued solution of the differential equation x dot equal to x. We now show that this complex valued solution gives rise to two real valued solutions of the equation x dot equal to ax. Suppose first let us prove this lemma, let x t equal to by t plus I z t be a complex valued solution of x dot equal to ax. Then we shall see that by t and z t are also are real valued solutions of 1. So the equation 1 is dx by dt equal to ax t. Let us put x t equal to by t plus z t in this. So d over dt x t plus x t is equal to by t plus I z t equal to a times by t plus I z t. So when you differentiate this vector valued function, what you get is dy over dt plus I dz by dt equal to a by t by matrix multiplication properties, so a by t plus a z t I. Now equating real and imaginary parts both sides, what we get dy over dt equal to a by t and then dz by dt equal to a z t, and these two equations then tell us that by t is a solution of dx by dt equal to ax t and z t is a solution of dx by dt equal to ax t. So by t and z t are solutions of x dot equal to ax. Okay. So thus if x t is equal to by t plus I z t is a complex valued solution of dx by dt equal to ax t, then both by t and z t are real valued solutions of x dot equal to ax. So the complex valued solution x t equal to e to the power alpha plus I beta into t into v, which is b1 plus I v2, let us split into real and imaginary parts. Then the real and imaginary parts of this complex valued solution will give us the two real valued solutions of x dot equal to Ax. So, e to the power alpha plus I beta t I can write as e to the power alpha t into e to the power I beta t, which is cos beta t plus I sin beta t, and then here b1 plus I b2. Now, let us multiply these two complex numbers. So, e to the power I alpha e to the power alpha t, and this gives you b1 cos beta t, I square is minus 1. So, b2 sin beta t, b1 cos beta t minus b2 sin beta t plus I times b1 sin beta t plus b2 cos beta t. Hence, if lambda equal to alpha plus I beta is an eigenvalue of A with eigenvector v equal to b1 plus I b2, then by t is e to the power alpha t b1 cos beta t minus b2 sin beta t, and z t equal to e to the power alpha t into b1 sin beta t plus b2 cos beta t are two real valued solutions of the homogeneous system x dot equal to Ax. Now, further we notice that these two solutions are linearly independent. We can see that let us put C1 by t plus C2 z t equal to 0. Then what we get? We will get C1 times e to the power alpha t into b1 cos beta t minus b2 sin beta t plus C2 times e to the power alpha t b1 sin beta t plus b2 cos beta t equal to 0. E to the power alpha t is never 0. So, we can divide this equation by e to the power alpha t, and this will give you C1 times b1 cos beta t minus b2 sin beta t plus C2 times b1 sin beta t plus b2 cos beta t equal to 0 after dividing by e to the power alpha t. Now, let us collect the coefficients of cos sin beta t and cos beta t. So, we get sin beta t times what you get C2 b1, here we get minus C1 b2 C1 b2 plus C2 b1, and then plus cos beta t times C1 b1 plus C2 b2 equal to 0. Now, we know that sin beta t and cos beta t are linearly independent, therefore, their coefficients must be 0. So, minus C1 b2 plus C1 b1 equal to 0, and we have C1 b1 plus C2 b2 equal to 0. Okay. This gives us the matrix equation b1 b2 C1 b1, this will be this is C1 b2 C2 b1, this C2 b1. So, we get okay. So, we get here minus C minus b2 here C minus C1 b2 and C2 b1. So, this is b1. Okay, and then here C1 b1 plus C2 b1. Okay. So, we get here minus b2 b1 b1 b2. Now, this C1 C2 to prove that C1 C2 equal to 0, we need to prove that determinant of this matrix is non-zero. Okay, and what is the determinant? Minus b2 b1 and b1 b2. So, determinant of this is minus b2 whole square minus b1 whole square. Okay. Now, this is 0 if and only if b1 and b2 both are zeros, but b1 and b2 both cannot be 0 because b is a non-zero vector. Okay. So, this is not equal to 0. So, this not equal to 0 implies C1 equal to C2 equal to 0. So, we get by t and zt are two linearly independent real valued solutions of equation 1. So, these solutions are linearly independent. Now, consider the initial value problem x dot equal to 1 0 0 0 1 minus 1 0 1 1 x 0 equal to 1 1 1. So, eigenvalues of A are, if you solve the determinant of A minus lambda equal to 0, that is you have the equation 1 minus lambda 0 0, 0 1 minus lambda minus 1, 0 1 1 minus lambda. If you solve this equation, okay, then you will get, you can see here, you have this gives you 1 minus lambda times 1 minus lambda whole square, and then here you have plus 1 equal to 0. So, what do you get? 1 minus lambda, okay, and then here lambda square minus 2 lambda plus 2. So, you get lambda equal to 1, and then here lambda square minus 2 lambda plus 2 equal to 0 gives you lambda equal to 1 plus minus I. So, eigenvector for lambda equal to 1 we can find by solving A minus I v equal to 0. Then it turns out that B1 equal to 1 0 0, column vector 1 0 0, which we can write as the row vector 1 0 0 transpose. So, here x1 t is equal to e to the power t, then 1 0 0. Okay, so, this is what we have, one solution we have got. Now, for lambda equal to 1 plus I, we have to solve A minus 1 plus I times I into B equal to 0. Okay. So, what do you get? A matrix is this 1 0 0. From this we subtract 1 plus I throughout the diagonal elements. Okay. So, we get here 1 plus I, when we subtract from 1 0 0, we get minus I 0 0, and then we get 0 minus I minus 1, and lastly 1 plus I we subtract. So, 0 1 minus I, 0 1 minus I, B1, B2, B3. Now, here you can see here we have minus I B1 equal to 0, this is first equation. Okay. So, we get B1 equal to 0. Then we get minus I B2 minus I B2 minus B3 equal to 0. This is second equation, and third equation is B2 minus I B3 equal to 0. So, second equation, third equation gives you B2 equal to I B3. Okay. So, taking B3 equal to 1, B2 equal to minus 1, take B3 equal to 1, then B2 equal to I. So, we get B1 is 0, so 0 I 1. Okay. So, that is the eigenvector corresponding to lambda equal to 1 plus I. Now, the eigenvector, okay. So, then the solution is x t equal to e to the power 1 plus I t 0 I 1. It is a complex solution of equation 1. From this we shall find the two real valued solutions of equation 1. Okay. So, for that we need to write this as e to the power 1 plus I t. So, e to the power t, and then e to the power I t can be written as cos t plus I sin t, and then 0 I 1. Okay. 0 I 1 we shall write as the real and imaginary parts in that form. So, we have 0 0 1 plus I times 0 1 0. 0 I 1 can be written as a real part 0 I 0, real part is 0 0 1 plus I times imaginary part is 0 1 0. Okay. So, what we do when we multiply this will give us e to the power t times cos t into 0 0 1, then I square is minus 1. So, minus sin t into 0 1 0. This is the real part, okay, real part, and imaginary part will be e to the power t times sin t into 0 0 1, and then we shall have cos t times 0 1 0. So, if you write it, simplify it, then real part is e to the power t times, you see here we have cos t into 0 minus sin t to 0. So, we have 0, then cos t into 0 minus sin t. So, we get minus sin t, and then here you have cos t, here we have 0. So, this is real part, and imaginary part is equal to e to the power t times here sin t into 0, cos t into 0. So, 0 sin t into 0, cos t into 1. So, cos t, and then we have sin t into 1. So, we have sin t. So, we get two independent solutions of the equation 1 which are e to the power t 0 minus sin t cos t, and then I times 0 cos t sin t. So, x t can be written as e to the power t 0 minus sin t cos t plus I times 0 cos t sin t, and we get therefore the two by using the lemma, the two real independent solutions as x 2 t equal to e to the power t 0 minus sin t cos t, x 3 t equal to e to the power t 0 cos t sin t. So, they are the two real valued solutions of x dot equal to a x. The three solutions x 1 t, x 2 t, x 3 t are linearly independent because they are initial values. Let us calculate their values at t equal to 0. So, you can see here x 1 t, when you put t equal to 0 gives you t equal to 0 gives you 1 0 0, and here when you put t equal to 0, what you get 0 0 1, and here you get 0 1 0. Okay. So, the three vectors 1 0 0, 0 0 1, 0 1 0, we know they are form a standard basis of R cube. Okay. So, they are linearly independent vectors in R cube, and therefore, x t equal to e to the power t 1 cos t minus sin t cos t plus sin t, okay, is the solution of the given initial value problem. We need to use the fact here that x 0 equal to 1 1 1, okay. X 0 equal to 1 1 1 we have to use. So, for that what you do is you write the general solution. General solution is x t equal to c 1 x 1 t plus c 2 x 2 t plus c 3 x 3 t. Okay. We have seen that they are linearly independent x 1 t, x 2 t, x 3 t. So, in that then you put t equal to 0. When you put t equal to 0, you get 1 1 1 equal to c 1 times x 1 0 is 1 0 0, then c 2 times x 2 t is 0 0 1, and then c 3 times we have 0 1 0. Okay. So, we get here c 1, c 3, c 2. Okay. So, we get c 1, c 2, c 3 equal to 1, and so the general solution is x t equal to e to the power t 1 cos t minus sin t. We can put here c 1, c 2, c 3 equal to 1. So, we get the solution of the initial value problem. Now, let us note the following: if B is an eigenvector of A with eigenvalue lambda, then B bar is an eigenvector of A with eigenvalue lambda bar, if A is a real matrix. Okay. So, A B equal to lambda B if you have, then we can see A B bar equal to lambda bar B bar. Okay. Since A, so R you can say A bar B bar equal to lambda bar B bar. Okay. Now, A is real matrix, so A bar is equal to A, so A B bar equal to lambda bar B bar. So, lambda bar is an eigenvalue of A and B bar is the corresponding eigenvector. Okay. So, if B is an eigenvector of A with eigenvalue lambda, and A is a real matrix, then B bar is an eigenvector of A with eigenvalue lambda bar. Now, here we have seen that alpha plus for alpha plus I beta, if B1 plus I B2 is an eigenvector, then for alpha minus I beta, B1 minus I B2 will be an eigenvector from this result. Okay. So, x t equal to e to the power alpha minus I beta t B1 plus I B2. Now, if you simplify this, multiply this, you write as e to the power alpha t, then cos beta t minus I sin beta t, and then B1 plus I B2, and then you write it as real and imaginary parts. You see that e to the power alpha t B1 cos beta t minus B2 sin beta t, and B1 sin beta t plus B2 cos beta t. We get the real part as this, imaginary part is negative of this. Okay. So, we do not get any new solutions you see here corresponding to the eigenvalue lambda equal to alpha minus I beta. We get the same two real valued solutions as in the case of alpha plus I beta. The real valued solution in the case of alpha plus I beta were e to the power alpha t B1 cos beta t minus B2 sin beta t, and here we had plus B1 sin beta t plus B2 cos beta t. So, if we know that if x t is a solution, C x t is also a solution. So, minus does not give us any new solution. So, this is what we have. So, corresponding to alpha plus I beta, we find two real valued solutions of the vector differential equation, and that gave us all the three solutions together with the solution for lambda equal to 1. So, these are the two real valued solutions of one, and these two solutions are same as in the case of alpha plus I beta with eigenvector B1 plus I B2. So, that is all in this lecture. Thank you very much for your attention.